Okay, so I was saying that we had a easier time here, right? But there's one little issue with that easier time, and that easier time is that we're going to have to use logarithms, and that's going to make you sad. It's okay, but you know it's still a little sad. So let's see. Let's say I had a capacitor that charged up to 10 nanocoulombs, and then I connected it to a resistor that was 100 kiloohms, and it takes 10 seconds or 10 milliseconds for the capacitor to discharge to 1/2. So the current to reduce to 1/2. Actually, I think for this particular case it's the same 1/2, but that doesn't mean much. So you'll remember we had for this I equals I0 times e to the minus t over RC. RC was our time constant, and C is what we want. So we're definitely going to have to take a logarithm to get rid of this e here. To be able to do that, we have to get rid of anything that's multiplying the e. We have to divide everything from the e. We need the e alone on its own side. So we'll have e of t over RC is equal to I over I naught. Now that's fine. That's good. Why is it good? Well, we know most of these things, right? So e to the minus t, t is 10 milliseconds. 10 times 10 to the minus 3 seconds. R was 100 times 10 cubed ohms, and that has to be multiplied by C there in the denominator. And that's equal to I over I0, which is equal to, we said it takes that 10 milliseconds to go to 1/2 I0, so our initial thing, so that's fine. I want to get rid of that minus sign, so to do that, we just flip everything. So we don't flip this part actually. So let's try to do something with these guys. So I have now 1/10 times 10 to what? Times 10 to the minus 6, 1 over C, it looks like to me, is that right? Is equal to, I have to flip that, 2. Oh, I forgot my seconds over ohms. Those are important. Okay, so now I take the logarithm. So the logarithm of something to the e is the exponent. So we have 10 to the minus 7 seconds per ohm over C is equal to the logarithm of 2. And the logarithm of 2 is 0.693. A little bit less than 1. Remember, e is about 3, a little bit less than 3, so this should be a little bit more than 2/3. So that means we have C is equal to 10 to the minus 7 seconds per ohm over, is that over? Bring that over here. Bring that up, bring that down, right? Yes, it is 0.693, which ends up being 0.144 times 10 to the minus 6, and those are going to be farads. Yeah, 10 to the minus 6 farads. I should have an ohm in there. That should be a farad. That already happened here. All right, so, oops. So that was just plugging numbers in. So I took this equation that we gave you from the lecture, and I just plugged numbers in, and then we had to, do our little things, including the logarithm to get rid of the e, right? We need to isolate that e, so it's e to the something is equal to something else. And then we can take the logarithm of both sides, so the logarithm of e is this something is equal to the logarithm of that something. So that's the hard part there. And then we do more, math stuff with our calculators. And their calculators eventually tell us we have 0.144 microfarads. Why do I use 0.144 microfarads? Because nanofarads aren't really used. That's what they use in industry, is they'll use 0.144 microfarads as the rating for the capacitor. Okay. So I just wanted to put that in, culturally, to make you feel like you can talk to your electrical engineer cousin. All right? I will talk to you later. Bye now.